Here we go on Chapter 1, Section 1. And again, we're looking at building blocks of algebra, the real numbers, and order of operations. So here's the building blocks of algebra. We've already talked about these. So first of all, numbers. We're going to dive into real numbers. The real number system is made up of sets of numbers, and we're going to get into those. Variables, second building block of algebra, letters that represent some unknown number or numbers. And finally, operations. So the operations that we are going to look at are addition, subtraction, multiplication, division, and exponents. I'm going to abbreviate here, just exponents. So let's dive into numbers. So we're looking at numbers that are what we call real. And there's a system of real numbers that is made up of different sets of numbers that all share certain characteristics. Now, before we dive into those sets of numbers, let's talk a little bit about the number line, because that's going to help us organize and understand these different kind of sets of numbers. So a number line is a horizontal line. Typically, we label the middle number as 0, use a hatch mark, and we can have to the right hatch marks that represent positive numbers. And also to the right, we have an arrow. That arrow means that it continues on without end, and we represent that idea of going on without end as infinity. So let's talk about infinity a little bit. It is not a number. It's not a real number. It's not any other kind of number. It's just an idea. And it's particular in the idea that something has no end. It is unbounded. It is going to continue to go on and on and on and on. And we use that infinity symbol to stand for that. And also the dot, dot, dot. We call that an ellipse. All right, if that is after something, it indicates that it's going to keep going and there is no end that we can identify. Okay, so that's going in the right direction. We start at 0, we go to the right, it's positive. The numbers are above 0, they're greater than 0, they are positive. And we go to the left of 0, write in hatch marks, and we've got negative numbers. So I'm just going to label a few numbers there. And to the left, that arrow tells us that it continues to go in that negative or left direction to negative infinity, which again is not a number. It's just this idea that it's going to continue on without end. So now let's go back to the sets that make up the real number system. First set is natural numbers, and they are the numbers that are used for counting. And these are often the first numbers that we encounter in life. And when we count, we start with 1. And then we go to the next whole number of 2, 3, 4, 5. And we could continue counting forever. So that dot, dot, dot there means that that list continues on without end. It goes to infinity. So natural numbers are the numbers that are used for counting. They are positive and they don't include 0. If we want to represent natural numbers on the number line, we would just put points at those numbers. 1, 2, 3, 4, and the arrow indicates that that's going to continue forever in that positive direction. The next set is whole numbers, which are comprised of natural numbers and adding to that the number 0. So if we write that out in set notation, we're going to start at 0 and then 1, 2, 3, and on and on and on. So on the number line, it's the same as what we had for natural numbers. We're just going to also include 0. Now we can also represent these sets as a picture. So we started off with natural numbers. If we let that rectangle stand for all of the natural numbers, then if we want to now show the whole numbers, we see that natural numbers are included in whole numbers. So natural numbers, 1, 2, 3, etc., and then whole numbers adds to that a 0. So natural numbers are inside of the set of whole numbers. So that means that every natural number is a whole number. 0 is a whole number, but not a natural number. The next set is integers, which is the set of whole numbers, and the negative natural numbers. So far, we've only had positive numbers and 0. So now we're going to add negatives, and that's going to give us the set of integers. So the set of integers includes the whole numbers. So 0, 1, 2, 3, etc. But we also want to go the other direction. -1, -2, -3, and I didn't give myself very much room, but it continues in the negative direction without n to negative infinity. On the number line, right, we're going to include those whole numbers, and then also include the negatives of those counting numbers. Okay, and it extends in the positive direction to infinity and the negative direction to infinity. And if we want to look at the picture of the sets that we're building, we have that natural numbers, and then whole numbers include natural numbers, and now we have integers, which includes whole numbers and natural numbers. So all natural numbers are integers, all whole numbers are integers, but not all integers are whole or natural numbers. Before we go on to the next set of numbers, which is rational numbers, I want you to notice that all of the numbers so far have been on numbers, on the hatch marks that represent a particular number. So we haven't put anything in between numbers. We have no fractions, no decimals, or decimals that are non-zero to the right of the decimal point so far. The next set of numbers is rational numbers, which includes numbers that can be written as fractions, like p over q, where p and q are integers, and q in the denominator, that cannot equal 0, because we're going to talk about this a lot. That would make it undefined. Let's look at some examples of rational numbers. 3/4. 3 and 4 are both integers. 4 is not equal to 0, so that would be a rational number. We can put that on the number line. It's about right there, and it's not on one of those hatch marks because it is a fraction, and so we don't have a labeled hatch mark for it. Another example, we can have a negative, let's just flip that over, -4/3. And here's another example. 16/7. 16 and 7 are both integers, and so that meets the criteria of a rational number. So another thing about rational numbers is in decimal form, they are one of two things. They either repeat or they terminate. So let's go to our examples and let's see what they look like when we write them in decimal form. So if we plug these into the calculator, we can get 3/4 is equal to 0.75. We can write down all the decimals that show up on our calculator screen. When we plug in 3 divided by 4, we get 0.75. My 5 is a little weird. Let me redo that. There we go. And what about -4/3? So if we plug in -4 divided by 3, we get -1 point, and then we get 3's, and it just keeps on being a 3. Okay, the first one, 3/4, where it's just 0.75, we call that an example of a rational number that terminates, because we can write down all the decimal places. So if we go down here, definition of terminate, it is possible to write down all the decimals. It does not go on forever. But the -4/3, that threes, we're not going to be able to write down all those threes. They're going to keep being one three after another, and we would just keep writing threes forever. So fortunately, there's kind of a way to write that that's a little cleaner, and we put a little horizontal line over the thing that repeats. So that's telling us that that's -1 point repeating 3. So you have a repeating decimal if a single digit like this, the 3, or a block of digits to the right of the decimal place repeats. So an example of a repeating decimal that's not just one digit would be something like 1.2535353, and it kept going. So what repeats is just the 53. So we could write that as 1.253. Now, when we go to put the line over the repeating block, it's just the 5 and the 3 because the 2 doesn't repeat. That just shows up one time. Now, let's go to our last example up there, 6/7. If we write that in decimal form, all right, plug that into your calculator, you get 2.28517. Sorry, let me go back here. 285,714. 285,714, and it just keeps going, okay? But what repeats is this right here. So we could write that as 2.285,714. To show that that part repeats, we put a line over that entire block of decimals. Okay. So rational numbers, they can be decimals, and if they are decimals, they repeat or they terminate. If we want some other examples of terminating decimals, we could say 1/2, because we can write that as 0.5. Or we could also say we've got 2/5, which would be 0.4. It terminates. So now we can see that rational numbers includes integers, whole numbers, and natural numbers. So let's take, for example, the natural number of 2. Okay, so it's a natural number, we count with it. It's a whole number, it's an integer. Well, we define rational numbers as being written as a fraction. Well, how do we write 2 as a fraction? We can take any whole number and write it over 1. So the p, the integer on the numerator, is 2, and q is 1. We can do that with any integer. Let's take -1,245. All right, that's just an integer. If we want to write that so that it's clear it's a rational number, we just take it and put it over 1. So any whole number, any integer over 1, right, it shows that it's a rational number. So integers, whole numbers, natural numbers are all rational. Now, what about 0? So we said that q could not equal 0, but p can be 0. And if p is 0, q can be anything. It can be a 1, and that's 0 over 1 is equal to 0. 0 over -5 is equal to 0. 0 over anything, as long as it's not 0, is just equal to 0. The last set of numbers before we have all of our real numbers is irrational numbers. They are numbers that are not rational. You can see in the diagram that it sits next to the rational number set, and there is no overlap. So in decimal form, we can define irrational numbers. In decimal form, they are non-repeating and non-terminating. So we can never write it down exactly in decimal form if it's a rational number. So let's look at some examples. All right, any square root that's not a perfect square is an irrational number. In decimal form, it's going to be non-repeating and non-terminating. So square root 2 is 1.4142135, and it keeps going. It doesn't repeat, doesn't terminate. Okay. Another example of an irrational number that shows up a lot in math is pi. So we know some of those numbers, right? 3.14159, and it keeps going. There's no repeating and no terminating. So keep in mind that pi is irrational, and anytime we have a square root of a non-perfect square, it's an irrational number. So it means that we're not going to be able to write it down exactly, which is why I like to just keep square roots as square roots and just use pi for pi. Now, irrational numbers and rational numbers together make up all real numbers. That means that real numbers are either going to be rational, they can be written as the fraction of two integers, or they're irrational, where their decimals are non-repeating or non-terminating. Let's look at real numbers on the number line. We haven't looked at the number line for some of the other sets of numbers, but when we have every real number, that means that every single number, every single point on that number line is included. So to represent all real numbers, we go from negative infinity to positive infinity. Every single point on that number line represents a real number, and every real number is represented by a point on that number line.